Okay, so our next panel is going to be on in-building communications. It's a really important topic. We've got 5 wizards here. I'm not going to have time to introduce them all, but they will be introduced. I'll introduce the panel moderator, who is Rob Lopez. I've known Rob for a number of years. He's the principal and owner of RLA Communications Engineering, which specializes basically in in-building, surprise, surprise. He worked for Motorola, started right out of getting his BSEE from New Jersey Institute of Technology, and then he got his master's degree in engineering management from the same school. In 1989, he joined RCC Consultants and became a senior vice president there before he joined Black & Veatch as Director of Public Safety Consulting and Distributed Antenna Systems. Rob's a member of numerous societies, including RCA, IEEE, APCO, and the National Society of Professional Engineers. Rob.
Thank you, everyone. Thank you, esteemed colleagues. Thank you to the RCA. I'm going to keep these opening remarks very brief. We all know what this topic is about. I think the previous panel actually opened up some questions, because these are questions that our clients have also been asking, is what is 5G going to look like for the indoor? Scott Schober, President CEO of Berkeley Electronics, who will be talking about various types of testing and validation mechanisms for the indoor space. So let me just briefly, takes about roughly 5 minutes to talk about these individuals' backgrounds, so you get some idea as to the level of expertise that's up here. Representing JMA Wireless, like I said, it's Bassam Iskender. He's a systems engineer at JMA, has over 17 years of experience in the wireless industry. Bassem has seen the telecommunications industry change and grow from several different perspectives that include wireless carriers, engineering consultancies, enterprise customers, and as well as wireless integrators, and from OEM's unique perspective at the current moment. He has held engineering management, director level positions at Stream Wireless, T-Mobile, Sprint, Nextel, AT&T, Cricket Wireless, and among others. This gives him a key insight on the inner and outer workings of the industry. To the core, Bassem is an RF engineering expert. He specializes in site design, capacity, optimization, and building DAS and outdoor small cells engineering. Bassem is a champion of value engineering to find the most cost-effective and technically sound solution available to meet customer requirements. Following him will be Alan Leffler. Alan is with RF Filtering and Indoor Booster Amplification Systems Designer Manufacturing Company, EMR Corp., where he is a sales manager. He's a 40-year land mobile radio industry veteran and a Radio Club of America fellow. He has authored articles, white papers, and publications about applying wireless radio solutions to increase safety, efficiency, and productivity in various applications. He's a radio amateur, call sign N7WYE, and lives with his wife, Karen, in Austin, Texas. Following Alan will be Doug. Doug represents Squan. He's a director of DAS design and implementation. He's a DAS systems integrator based in Englewood, New Jersey. Doug is also an industry veteran with over 25 years of wireless industry experience, including jobs with software and hardware vendors, wireless carrier experience with AT&T, as well as having extensive DAS and public safety communications consulting experience. He is currently responsible for the design, testing, and commissioning of in-building DAS networks for Squan. He has worked on numerous different venues in New York City area, including both residential and commercial properties. And if I recall correctly, Doug, you're involved in one of the largest real estate development projects in the country here in Hudson Yards. Following Doug will be Mr. Scott Schober. Scott is the president and CEO of Berkeley Veritronic Systems, or BVS, a company that celebrated its 44th year in business based in New Jersey. BVS is a privately held company and a leading provider of advanced test and security solutions. Since the beginning of Mr. Schober's tenure with BVS in 1989, the company's product line of wireless testing and security instruments has increased to over 100 products with a core focus on Wi-Fi, cellular, WiMAX, LTE, IoT, and advanced radio services. He's an experienced software engineer and has developed cellular and LMR test instruments used for measuring, optimizing, and plotting signal coverage. Scott's recent focus has been in the development, patent pending, of BVS's cell phone detection tools used to enforce a no cell phone policy in various markets, including government, corporate, military, educational, correctional, and law enforcement. Mr. Schober is a highly sought-after subject matter expert on the topic of cybersecurity and wireless technology for media appearances and commentary. He is often seen on ABC News, Bloomberg TV, Al Jazeera America, CBS, CCTV America, CNBC, Fox Business, Fox News, amongst others. His precautionary advice is heard on dozens of radio stations, such as National Public Radio, Sirius XM Radio, and Bloomberg Radio. Scott educates different types of businesses and organizations on how to prepare for future cybersecurity and corporate espionage-related problems. So with that, I'd like to introduce our first presenter, Mr. Bassam Iskender.
Good afternoon, and thank you for having me. It's an honor to be here. I work for JMA Wireless. We are an OEM of antennas, connectors, and most interestingly to me, DAS systems. Over, I guess, the last 4 or 5 years, the in-building wireless space has kind of evolved on its own. It started with the carriers building out DASs where they felt they needed coverage, but at a certain point, they had to have the corporate world step up and carry that ball, which brings us to the point of this presentation. One of the biggest expenses of a DAS is the RF source. How are the carriers expected to fund a DAS, and if even not funding a DAS, how are they expected to put a base station into every single in-building system? So we thought about this at JMA, and what we took a different approach. Some companies thought of the small cell world as a start to funding, to covering in-building systems using a small cell solution. What we dubbed our EDAS solution is basically using a small cell as an RF source to leverage it and its IP network backhaul to as an RF source to an in-building DAS system. What it does is you no longer need to get the carriers involved. There's available that you can go out and buy from the carriers right now, and no longer need to get them to use their base stations. That's basically the
Radio doesn't work the greatest when you get below the surface on those things. I'm going to just talk a little bit about the difference between what we know in our industry as channelized and Class A and Class B boosters. Class A booster is a channelized one. A lot of use, like for mobility or cell carriers, they want to exclude other users or other carriers from getting into the building. You see a lot of that. It might be also useful in a higher RF environment for public safety or enterprise applications where you just got so much RF and you got to manage it. Generally digital compatible. They're available in many bands, but maybe not in VHF is what we're seeing. And you can use other methodologies per the FCC's definitions to achieve channelization or Class B functionality or Class A functionality. using what are called selective or crystal filters to get down to a 75 kilohertz window. So you also have to design for what other might be needed in terms of mutual aid and making sure that if you do a deployment using channelization, is there any succession plan? What happens is, guy gets into a position, he's an administrator, and 5 years later he moves or retires or leaves and goes into another position. Someone's got to maintain Class A boosters and the records so that if, let's say, you're in the Bay Area, California, they have a channel change. And if you look at in the Washington Radio reports the number of line items for licensees in the Bay Area, California, those 11 counties, I think it's like 4,400 line items, or there's a lot of licensees of channels. So that's all got to be maintained. They're generally a little bit more difficult to employ or deploy, so you got to know about that. And then we spoke about the record keeping and higher cost. Class B, on the other hand, they're non-channelized, and what they use is filtering for doing that. Digital compatible, all the bands from VHF up through 900 megahertz. They're pretty easy to design and accommodate nearby AHJs that are involved. Easy for channel changes, and they use what's called broadband filtering. They'll have a passband for selecting the channels that are there, and it can be as little as like 75 kilohertz. A lot less complicated. It's not really designed particularly for carriers and cellular, lower cost. If you want some help in doing these designs, you need a resource. We do this kind of work all the time. We work with partners, we work with distributors, work with a lot of people. We'll collect a lot of data, ask you a lot of questions. You'll sometimes be driven crazy by our engineering folks that want to ask all about how this system's going to work, what the frequencies are. And this is just maybe about a quarter of the farm that we'd be asking data on. We'll ask for some readings if you can get it. People that really furnish more detail about that, we have more to go on. So that's a good thing, because you don't want to populate and put antennas into areas where they're not required. And in a lot of cases, you get above the 4th or 5th floor, or even in high rises, the two-way radio systems work out just fine. So there really isn't a need for that unless it's mandated at a certain coverage level. Here's an example just showing what we'd look for, showing where to put the antennas, splitters, dividers, and how it would lay out, where maybe the equipment closet would be. We'd, again, ask you for that kind of information when you're going for it. Here's a schematic. This is just showing 800 megahertz. On the left side of the diagram is coming from the donor site, a Yagi antenna, quantum reflector antenna, pointing at the source, going through a series of filters, amplifiers. It's got a power supply in between, and it's got a bidirectional path going to a splitter. Then it's got dipole antennas, line taps, and a bunch of other equipment that would go through the DAS, or this is a coaxial distributed antenna system. And again, you have signal flow paths that are going in one direction and then coming back in the other way. So it's pretty cool. If you need 700 and 800 megahertz for doing it, these are very popular right now. A lot more talk about FirstNet and what the bands will require. It's just another series of filters that are in the group to allow accommodating the additional band here. This one here shows about 11 megahertz of width, so it over accommodates for what that require is. It's tied together with an isolator, or isolators, excuse me. As far as what a DAS system looks, VHF. Is my time up? I like that. It's very good. You know, when you're in sales and marketing, you tend to prattle. And when that happens, it's fortunate for these things, these devices, to have these wonderful capabilities of limiting our time. So here's just one showing in the standard gray. These are available in colors that you might like for your site. This is our beautiful EMR gray color. Really works out nice. If you're looking for a mandated battery backup, we got that capability too. Also in a gray, or I'll even show you in this next slide. It's coming up, Rob. Don't get excited. Look at that, red. Everyone loves red, and you can have it silk screen in the name of your department, because in a lot of cases they're regulating or requiring as part of the regulation that a fireman or a first responder can see that there is a unit in place when he walks into a building. So a lot of different features from the IP-based power monitoring right under, even if it's really super big, which some of the VHF ones can be rather large, it will have rack mounting available. So it'll be just kind of big. And here's there. Crystals are really key in these for selectivity, so that's important. And do that. I'm over time. Okay, so you got some antennas. We got there. We can tie in with fiber desk if you need that. Oh my gosh. I feel that there's going to be a hook coming out next. I'm just saying, and I'll explode. Look at this here. Okay, Rob, you got your way.
Sorry.
We also do this thing. Thank you. Wait, one more. We got white papers if you want on our website to tell about it. It's getting louder and louder. This is very disturbing. But
Oops. Sorry. There you go.
Okay, hello everybody. My goal in this presentation, besides avoiding that creepy music, is to give you guys a quick little education in my now 12 and a half minutes of time. We're gonna, that's okay. We're gonna talk about a very specific piece of in-building wireless, and that's the design of DAS and the importance of creating an accurate model for an accurate design. How do I do this? Down. Okay. Really quick about my company. Company's called Squan. We're what's called a DAS systems integrator. We do pretty much everything from soup to nuts related to in-building distributed antenna systems, specifically on the commercial side. We do design. We're IB-Wave certified, and I'll talk for a minute about that on the next slide. We do construction, we do testing, we do commissioning, we do maintenance. So we're kind of like to think of ourselves as a one-stop shop. Okay, that's enough of a commercial. Now to get into the good stuff. So creating an accurate model in IB-Wave is really paramount to creating a good design. And before I go too much further, can I see by a show of hands how many of you are familiar with IB-Wave and what it does? Okay, so maybe about a third of the audience here. Let me just spend 30 seconds just giving you a high-level overview. Antennas, cabling, electronics, and it's got built-in ray tracing propagation models that let you predict what the coverage is going to be based on how you lay out the system and, importantly, how you model the system. So what's shown here on the slide here is a portion of a floor plan of a building that we've worked on. And as you can see, let's see if this works. Yeah, so the different elements in the floor, the drywall, metal around the elevators, concrete again in the core of the building here, wood, the red along the doors are wood, and glass along the outside are all things we set up when we build the model prior to doing the design. Now, it's very important to validate the model, okay? So you do that in two ways. First way is doing a survey of the building. Now, this works fine with existing buildings, but a lot of times you're working on new construction where you need to get very familiar with the architectural plans of the building and make sure you've got the right materials in the right places. Also, it's highly recommended to do field testing, where you're basically taking a CW generator at several locations throughout the building, testing different materials to validate. And you can see we actually collected a lot more data than is shown, but we averaged the data over 20 wavelengths. So you see this was done at PCS, so it's about every 5 feet you see a data point. And you can see there's some issues here in terms of if you look at just the colors of the actual data points versus the predicted. In some areas you're pretty close, but in some areas like up here, you're quite far off in terms of what the actual is versus the predicted. And in this specific case,
has been in excess of like $250,000 high-capacity base station using a scalable solution based on the EDAS approach presented by JMA. And then following that, the land mobile radio and public safety in-building solutions are still utilized to this day that address both analog and digital solutions as presented by Alan from EMR. And then addressing the sort of industry standard approaches now for in-building design provided by Doug from Swan, who has, yes, real-life experiences in terms of validating those models, and of course verifying the performance of those models and those designs using the tools as presented by Scott. So at this point, if you all have any questions with respect to the topics that have been covered today, please fire away. Yes, sir.
I had a question for Alan. Alan, how do you know if the antenna is failed? What technique do you use to measure the antenna failure?
We're using a form of a directional output and seeing sampling at the output of the bidirectional amp that it's operational.
You on the transmit side or the receive side of the boat?
You also want to you want to measure in a building, but you also may want to do it multiple times. Oftentimes somebody may go in after the staff is out. If the building's loaded with a lot of people and obviously a lot of wireless devices, it's going to be very different characteristics than after hours. So taking all of those things into play and perhaps even coming back and do a benchmark at another time, alternating a bit, and that way it gives you really a true baseline to base that on to understand where's your noise level, what interferers do you have there. You might have to hunt them down a little bit, get a spectrum analyzer, some other tools, but it makes it a lot easier than when then you can propose something to your client and start actually building out. You'll save yourself a lot of money in the long run and hassle.
That's a good point. So we hear a lot of the term of bring your own device. In this case, is bring your own interference, right? That you try to measure. Good point.
I want to answer your question from a different perspective. Today's LTE networks are adaptable. So what they do is their modulation scheme changes depending on the interference level. What we've seen is when you have higher noise floors, the LTE goes from 64 QAM to 16 QAM and even to lower orders of modulation, and that has a dramatic effect on your throughput. You can have the same coverage level, so when you design to coverage thresholds, that's one piece. But when you design, as Rob was saying, to interference threshold that you have to overcome by this much, so you have a dominant server, that helps a lot. Of course, there's some things that you can control, some things you can't control. We had a recent stadium design that something happened in the third quarter of a game that all the data across the 1900 band, I think, went very, very sour. And it lasted for half an hour during the game, and we didn't know why. So the next game, we sent someone out to find out. All the carriers came to us and said, "What's wrong with your equipment?" And it turned out to be that they played something on that scrolling LED screen that caused the interference levels to spike. And it wasn't just the screen; it was the content. Yeah. So.
So is the vulgarity?
Well, the solution was a filter, but that's some of the things that you can't control, and it affects the data. It's the bars alone.
That was a good point. Rob, what another thing that we find out in gas systems and BDAs in particular, real pain, is that people say they'll give us a spec, well, we need a 80 dB gain unit. And we say, no, you don't need that amount of gain. And they demand it, and invariably they're going to attenuate that signal and down to 50 or 60 dB because there's just too much gain. That's our biggest problem. The nemesis that we deal with pretty regularly, 1 or 2 a month, the guy gets the BDA out and it's overdriven and it goes into oscillation because it's not isolated from the input donor source into the DAS. and it is a common problem. Because it's like going out and buying your newest Infiniti G37, and it's got 330 horse, but you didn't get the all-wheel drive, and it just can't get all that power to the road. Not a good thing. So, just what I see.
Thank you for your thoughts. Yes, very good. So I think we're at the 3:45 mark. So if there are no other questions, we're going to hand things off back to John.